In these videos, we're going to look at miscellaneous approaches for nonlinear ODEs. There are approaches that can be used in some situations, but not in others. And it's going to be a bit up to you to see when something is possible and when it's not. We're not going to be testing this during the midterms or the final exam. The first method we want to look at is the integrating factor method. So we know that when we're looking at first order ODEs with non-homogeneous with non-constant coefficients, we can explicitly write solutions, but it's sometimes kind of hard. So let's look at a way to find the solution in an easier way. We know that x prime equals to f of x. It's fairly easy to solve. So z is just the integral of f from 0 to x. So if we're looking at our first order ODE with non-constant coefficients and non-homogeneous, maybe we can offset this whole thing by a factor sigma that makes our job easier. So if we offset everything by a factor sigma, we have sigma y prime plus sigma py equals sigma q. And if we choose sigma well enough, then our left-hand side is actually the derivative of sigma y. If this is the situation, then we can solve for sigma y being our new unknown. This is easy to solve, so it's the integral between 0 and x of sigma q. And then you can invert sigma away, so y is sigma at the minus 1 times the solution of the previous equation. Can we find sigma such that this can be handled? Turns out that we can. If we want the derivative of sigma y being equal to sigma y prime plus sigma py, then we can compute it all out. So the derivative of sigma y is sigma y prime plus sigma prime y. Then we're solving for sigma. We can simplify the sigma y prime on the two sides. We have sigma prime y equals sigma py. We can simplify the y way. So we have sigma prime equals sigma p. We can divide everything by sigma. So we have sigma prime divided by sigma equals to p. We know that is the derivative of the logarithm of sigma. So we have something here fairly easy on the right-hand side. We can write the logarithm of sigma as an integral on p. So as a general statement, sigma is a times the exponential of the integral of p. By the way, this combining with everything that we did before, this retrieves the usual formula, but it might be an easier way to approach things than what we have usually done. We have seen the method of variations of parameters many times, so this is just a recap of things we have seen already. The idea being you want to solve a more complicated problem. Instead, you assume that is just a specific case of a simpler problem. You know the solution of the simpler problem, and you take the assumption that the simpler problem solution can be changed a little bit to find the solution of the full problem. So let's, for example, look at y second plus 2y prime plus y equal to 0. If we do the method of characteristics, we notice that it has a double root equals to -1. So we know that one solution of it is yx equals a times exponential of -x. And by the method of variations of parameters, we say that a now depends on x, and we try to solve it that way. Now a new method that we haven't seen before, the method of clever transformation or change of variables. This is definitely a pro move. So requires a lot of understanding of the equation you're looking at, quite some intuition of how you want the solution to look like. So it's definitely not a trivial application of anything. But there are some known equations in which the clever transformation allows you to find solutions. So let's look at some examples. The first one being the Bernoulli equation. It's y prime plus pxy equals qx times y to the n. We make a change of variables. In this case, n is strictly bigger than 1, otherwise we could simplify things out. We may take a change of variables. We introduce v being y at the power 1 minus n. Then v prime is equal to 1 minus n times y at the power minus n times y prime. So we have a relationship between y prime and v prime. Let's plug v prime in our unknown and transform everything as a function of v. So we went from an equation that is in y, that has y prime and y to the n, to now an equation that is in v, that only has v prime. Everything else got simplified out. So now we can solve our equation because we know how to solve this type of equations, and if we can find v, then we can find y. And we can solve the Bernoulli equation for any power of y strictly bigger than 1. Let's look at another equation, the Riccati equation. Y prime equals pxy squared plus qxy plus rx. So is the Bernoulli equation for n set equal to 2, in which we have an extra term r. We take as assumption, and then we'll try to justify that y can be written as the sum between capital Y being a particular solution and 1 over u. So y prime is capital Y prime minus u prime divided u squared. And we plug this in the full solution, and expressing this in full, we notice how, well, capital Y returns in the same format as the Riccati equation itself, so we can simplify it out. And now we have an equation that depends on y and u, in which, by simplifying the setting, we have u prime plus a function of x multiplied by u equals minus px. So this is a non-homogeneous, non-constant coefficient, but it's first order, so we know how to solve these equations. Caveat, if we know capital Y, and we still don't know how to find capital Y. And by this I don't mean that this class doesn't know how to solve it. By this I mean there is no general way of solving it. So while we do have a trick to how to find the general solution, capital Y still is unknown in a general setting. Let's look at another. This is a group of ODEs. They're called separable ODEs. You have a first order ODE in which y prime is equal to the product of two functions, one being a function of only x, the other being a function of only y. By Lagrange formulation, you can write y prime as dy over dx, and then you're splitting dy on one side, dx on the other, and you separate the variables. So you have everything relate to y on one side of the equation and everything relate to x on the other side of the equation. Now, you can take, there is a typo, capital Y should depend only on y. Now you can take the integral of both sides, and it makes sense. Let's look at an example for this case. You have y prime equals minus y squared. In this case, what is the function depending on x? It's just a constant. So you take all that depends on y on one side of the equation, giving you minus dy over y squared, and everything that depends on x on the other side of the equation. That is just 1 times dx. And then you integrate on both sides, and you retrieve 1 over y plus c2 equals x plus c1. You shift things around, and you retrieve y equals 1 over x plus c. Let's look at another equation. Y prime equals 4x divided 1 plus 2 exponential of y. So we have a function that depends on x, that is 4x, a function that depends on y, that is 1 plus 2 ia dy. We take the function that depends on x on one side, the function that depends on y on the other side. We take the integral on both sides, and we can solve it again. Solve it again. It's a bit more unclear than it was before, because now we have we have a formula for y, but y is not explicitly defined. So we have y plus constant times exponential of 2 over y equals 2x squared plus a constant. So we have something that depends on x on the right hand side, but on the left hand side we don't have a simple y equal to x. Let's look at a new category, exact differential equations. By this, it's a category of equations in which y prime is equal to a fraction between two functions depending both on x and on y. Let's look at another problem, and let's see how that then connects. Let's look at a function f of x and y that is constant, that is equal all the time to a constant. Then the full derivative of f is the partial derivative of f dx times dx plus partial derivative of f dy times dy, all of this equal to 0. So if you shift things around, you'll notice that you can write dy over dx equals to minus the fraction between the partial derivative of f with respect to x and the partial derivative of f with respect to y. So if we can find an f such that the partial derivative of f with respect to x is equal to the top part of our fraction in our original ODE, and the partial derivative of f with respect of dy, with respect of y, is equal to our denominator in our original ODE, then we can retrace things back. When can this happen? Dy over dx equals minus the fraction m over n can be written as dy over dx equals minus the fraction between the partial derivatives of f only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So we are swapping the partial derivatives. The idea of the proof is that if partial derivative of f with respect to x is equal to m, then the partial derivative of m with respect to y is equal to the second derivative, partial derivative of f with respect to x and y. In a similar way but shifted, we can do for n, if the partial derivative of f with respect to y is equal to n, then the partial derivative of n with respect to x is equal to the second partial derivative of f with respect to x and y. These two terms, the previous one and the second one, if f exists and is second order differentiable, should be the same term. Let's look at an example of how this can work out. We have y prime equals a fraction between sine of y and 2y minus x cos y. We can write it as dy over dx equal the same fraction. Then we multiply everything by 2y minus x cos y and by dx. So now we have 2y minus x cos y dy minus sine of y dx equal to 0. If we can write all of this as a full derivative of a function equal to 0, we are good. And this function, and we can see, is minus x sine of y plus y squared. Let's first check if this function actually exists. So we define m being minus sine of y and n being 2y minus x cos y. We take the partial derivative of m with respect to y. We take the partial derivative of n with respect to x. And in both cases, we retrieve cos of y. So by the theorem, capital F exists. What about combining this exact differential with the integrating factor? So let's assume that n dy plus m dx is not equal to 0. But we can find a sigma such that sigma n dy plus sigma m dx is equal to 0. That means that we can write the partial derivative with respect to y of sigma m being equal to the partial derivative with respect to x of sigma n. If we're able to find this sigma, then we can retrieve the exact differential approach that we just did. Honestly, finding sigma is usually quite hard because we need to find a sigma that depends both on x and on y. The easier approach, if possible, is to try to find a sigma that depends on only one variable, so that is trivial in at least one of the two directions.